Hello, I'm going to present the work entitled Segregation of Heterogeneous Swarms of Robots in Curves. This work was done by Edson Ferreira-Filho and Luciano Pimenta. They are from the Universidade Federal de Minas Gerais from Brazil. Swarms of robots are inspired by behaviors found in nature. Swarms of robots are systems composed by a number of agents that interact and cooperate to reach a common objective, like this school of fish that is escaping from a shark. There are several advantages in those systems, such as individual fault tolerance. This means that if a fish gets eaten, it does not affect the global task, which is to escape the shark. Those systems are also flexible, in the sense that it can adapt when the task needs it to. Those systems are scalable. In this example, fish can join or leave the school without affecting the global task. Now the problem definition. You want to segregate robots into groups, where each groups contain only robots of the same type. In those examples, I'm segregating robots into groups attached to a line and to a strange curve. We can also segregate robots in the three-dimensional space. In this example, robots are segregated into groups containing only robots of the same type attached to an helicoid. In our methodology, there must be a group hierarchy in the system in which robots do not have the knowledge of the whole hierarchy, but they can compare the hierarchy when they are close enough. We are also assuming that there is an underlying connected topology. Therefore, robots can execute a consensus protocol through it. Finally, we are assuming that all robots in the system have the knowledge of the same open curve. The main idea of our work consists in use a formation control consensus to position robots near the curve and a heuristic that we proposed in which robots exchange information locally to decide where in the curve each group should be positioned. Now I will give you an example to explain the proposed heuristic. Consider a system with three robots divided in three groups represented with different colors. This system has the hierarchy shown in the figure. The purple robot is of the first group, the green robot of the second group, and the red robot of the third group. In this moment, only the purple and red robots are visible. Robots can exchange information in two different ways. Robots use an underlying connected topology so that they can run a consensus algorithm, and they can compare the hierarchy when they are close enough. Through the underlying topology, robots run a consensus that make robots move to the mean of their initial positions. In this moment, both robots believe that their groups are the first ones in the hierarchy, as it can see in those boxes. Now that the robots are close enough, they can compare their position in the hierarchy. The red robot now acquires the information that its group is higher in the hierarchy than the group of the purple robot. The red robot moves to a new position while the purple robot continues moving towards the mean of the initial position of all robots in the system. Now the red robot is in the new position while the purple robot is positioned at the mean of their initial position. Boxes are not robot memories. Robots can only make a comparison when they are close enough and not store information. Now consider that a third robot have arrived, the green one. The green robot believes that it belongs to the first group in the hierarchy and proceeds to move to the position where the purple robot is. When the green robot and the purple robot are close, the green robot realizes that it should move to the next position. When the green robot arrives near the new position, the red robot is already there. Both robots compare the hierarchy and the red robot realizes that it should be moving to a newer position. Now the system is segregated. These heuristics, together with a scheme that makes robots have sufficient meetings, guarantees that all the robots will eventually acquire the real position of its group in the hierarchy. This is one of the main contributions of this paper. This heuristic will be part of a formation controller as shown. We consider an error variable with the difference between the position robot's Q and the desired position. The desired position is composed of two terms. The term SDI will give the position exactly on the curve which robot I should go, and it's given by the heuristics in which the mean of the initial position of the robot is the beginning of the curve, and parameter di gives the length of the curve from its beginning. We also add a random component to this error so that robots do not converge exactly to the curve, but to a region near the curve. This scheme is done to avoid robots of the same group to have the same desired position. We use the error variable to position robots with a formation control consensus that also has a velocity dumping so that robots reach their desired positions and stop. We also have a collision avoidance term that does not interfere in the whole segregation scheme. We still have one problem. What should be the distance between groups? We have proposed in strategy to increase the distance while robots are close to robots of other groups. To guarantee that robots of the same group go to the same region, we use the connected topology to run another consensus so that all robots in the system agree with the same distance between groups. This strategy, together with the formation controller and the heuristic, will guarantee that robots of the same group converge to the same region and that they will eventually be far from robots of different groups. To validate our controller, we have performed 2D and 3D simulations as well as experiments with real robots. We show 4 2D simulations with different curves: one line, a spiral, a straight curve, and a senoid. One can see that in all cases groups achieve segregation. In 3 dimensions, we first show robots segregated in a line. You can see that groups keep segregated while closed from other groups. We also performed a 3D simulation in a helicoid. Finally, we present experiments with real robots with a spiral curve in which the system converges to a segregated state. You can see that robots of the same group have the same markers, and the curve in the bottom left shows that the segregation error goes to 0 as intended. This experiment is accelerated 2 times. We have presented an approach to the problem of segregating a swarm of robots based on the use of formation control consensus algorithm. We have shown a method with convergence proof with collision avoidance for 2D and 3D cases. Furthermore, we segregate groups based on the traveled geodesic distance on curves, which is a unique approach. Future work will focus on strategies to segregate groups of robots in which robots do not need to have the knowledge of a curve. I would like to acknowledge the Brazilian funding agencies that made this work possible. That was it. Thank you for watching.